framework for optimization of fibre preforms, and that's presented by Dr. Mikhail Matveev. You're on mute, Mikhail.
Thank you. Hello, everyone. My name is Mikhail Matveev. I will be talking about a numerical framework we developed for optimization of fibre preforms. This will cover part of the project Andy talked about at the very beginning. So as it was mentioned before, 3D reinforcements offer better mechanical properties in the through thickness direction and also can be manufactured to the near net shape. Angle interlock 3D fabrics are already used in the aerospace industry, in particular the fan blades in the LEAP engine manufactured by General Electrics. But again, the industry uses only several conventional architectures like angle interlock or orthogonal weaves. And in all of these architectures, warp and weft yarns are always orthogonal to each other. So there is a lot of room for optimizing the fibre architecture. You can optimize the weave pattern, you can optimize the toe size, but also you can create 3D architectures where warp and weft yarns are not necessarily perpendicular to each other. So there is a need for some sort of optimization tools to arrive to better architectures than it's possible now. So hence there are several research challenges: how to optimize internal structure of 3D composites, and then how to manufacture these reinforcements. The latter has been slightly covered by Prasad Patluri in his previous presentation, and I will talk about the optimization of the internal structure of 3D composites. To optimize the architecture of 3D composites, we developed a framework, a numerical framework, which consists of several steps. The first of them is creating model of a reinforcement using TextGen software. Then once we got the model of the reinforcement, we then move to the mesoscale simulations, where we can extract material properties of the reinforcement, be it mechanical properties like tensile stiffness and strength, or processing properties like permeability. But in this presentation, I will be only talking about mechanical properties. So once we've extracted material properties from the mesoscale geometry, we can move on to the microscale, where we simulate structural performance of an entire part as if it was manufactured from the reinforcement we are interested in. And when we evaluated the performance of the structural composite part, we then can pass it on to the optimization algorithm. In our case, we use genetic algorithm, which will then evolve the solution in sort of like a loop fashion, and will arrive to an optimum. So the main challenge is how to link the mesoscale properties with the macroscale properties, and also how to perform a multi-objective optimization. So to improve several properties simultaneously, or improve mechanical properties and processing properties simultaneously. So the first step in this framework is related to TextGen software, which is an open source software developed by the Composites Research Group at University of Nottingham. It's freely available at this website, textgen.sourceforge.net. And TextGen is a preprocessor used to model geometry of textile structures. To be specific, TextGen sits right in between the microscale modeling and macroscale modeling. At the mesoscale, where TextGen is used, we look at the internal structure of textiles. We look at individual toes and how they interlace with each other, but we do not look at individual filaments. Using TextGen and its graphical user interface, it's possible to create different 2D textiles, 3D textiles, including orthogonal, angle interlock, and layer to layer. And then it's possible to create input files, which then can be used for finite element solvers or for CFD solvers to predict material properties. What is important here is that it's possible to program TextGen to create these models in automatic fashion. So we can parameterize our model by several parameters and generate it on the in a batch mode, just driving it from an external program. And it's very important for any optimization framework, an ability to generate the models quick and without any kind of like user interaction. As I said, TextGen software is freely available from this website. You also can find the source code on the GitHub, along with the sample codes for scripting TextGen, and also tutorials on how to script TextGen. Since 2006, when the TextGen was released to the open source, there has been almost 50,000 downloads from all over the world. Now I'll talk a bit about multi-scale modeling, and primarily I will talk about how we can get from the mesoscale to the macro scale. So 3D woven composites and 3D composites in general are only 1 unit cell in thickness. So which means they are relatively thin compared to their in-plane size, where the unit cell is repeated multiple times in X and Y directions. So how to get macro scale properties from this unit cell? And actually, what properties do we actually need? If we extract only tensile stiffness, then actually we will see that the binder path has very little influence on the tensile stiffness or shear stiffness for that matter. But what about flexural stiffness? And flexural stiffness becomes important when we think how to model the composite at the macro scale. The most efficient way to model composites at the macro scale is using shell elements, because usually composite structures are relatively thin but have large in-plane dimensions. So we actually do need these flexural properties to model, for example, simple 3-point bending. But how to get the right properties for this model? To get the right properties, we need to apply specific boundary conditions to our unit cell. Three problems consist, three boundary conditions represent 3 in-plane deformation modes. One is the stretch in X direction, stretch in Y direction, and in-plane shear. And 3 other deformation modes are out-of-plane deformations, bending around X-axis, Y-axis, and a twist. And simulating these 6 loading cases will give us a generalized stiffness matrix which fully describes the composite material as a plate. In classical laminar theory, this stiffness matrix is often called an ABD matrix, and I'm sure that many of you are familiar with it. This work has been done in collaboration with Professor Shiguan Li from the University of Nottingham. Also, when we extract material properties using these boundary conditions, we will be able to get a bit of an insight on how much the binder path actually, how much influence the binder path has on the flexural stiffness. And we will see that just by changing the binder path without changing its weight, its toe weight, or something like that, we can increase flexural properties by 10%. Something we will not be able to see if we use only the first 3 deformation modes. So now I'll talk a bit about the optimization routine we use in this project. So when we talk about optimization, we have a particular problem in mind. And here we start with a design of a reinforcement and a part geometry. Here it is an automotive floor panel for which we want to maximize the bending stiffness with no increase of weight. In the optimization framework, we start with a parameterized model of the unit cell, where we parameterize toe sizes, number of layers, binder path, and orientation of each individual layer. We can homogenize this mesoscale geometry and obtain stiffness matrix, an ABD matrix, which we then pass on to the macro scale simulations, where we perform a finite element analysis on the structure we want to optimize. So in this case, we we apply bending load to this structure and obtain its stiffness, which together with weight form objective functions for the optimization. These objective functions used in the genetic algorithm to compare the designs of the reinforcement with each other. Then good designs will be mutated or tweaked slightly to get a possible improvement, and also good results or good designs will be crossed over. So good features will be taken from some designs, merged with good features of other designs, and again, the algorithm will see if it leads to an improvement or not. An important point here is that we do not limit ourselves to conventional architectures here. We do not optimize only, say, orthogonal weaves or angle interlock weaves. We relax the manufacturing constraints and we consider off-axis yarn orientations and different weave patterns and weave patterns which are not necessarily available from commercial suppliers. So in this loop, where we simulate mesoscale geometry, simulate macroscale response, and pass it all into the genetic algorithm, we get improved designs at every pass of the algorithm, and eventually we apply to a converged optimum for our problem, which will be a better design than we started from. So to continue this example, here we work together with Advanced Manufacturing Research Center to optimize performance of automotive floor panel. We wanted to maximize its bending and torsional stiffnesses for the given weight and thickness of the panel. And the constraint on thickness came from the fact that we have already had an RTM tooling and the cavity thickness was already predefined. To demonstrate the benefits of 3D composites, we considered two design spaces. One is a layout consisting of conventional non-crimped fabrics used in automotive industry a lot. And the second design space is multi-axial 3D preforms, something like this, where each layer of yarns can have any orientation, not necessarily 0-90. And on top of that, we have a through thickness binder, which can have different weaving patterns. So when we simulate this floor panel using finite element analysis, we will get the map of displacements in bending and in torsion. And if, for example, this panel was made out of aluminum, its performance would be represented by this dot. So certain displacement in bending and torsion. When we consider a composite made out of non-crimped fabrics, we can get different designs. So each of these dots on this graph represent a different layer made out of non-crimped fabric. And we see that some of the designs are actually better in both torsion and bending than aluminum part, which is quite natural. And on top of this improvement in the performance, we of course get the weight saving, just because it's a composite reinforced part, carbon fiber reinforced part. It's already lighter than aluminum. But can we do better? And if we consider optimized multi-axial 3D preforms, we indeed can do better. Again, each of these points represents a unique design of a multi-axial 3D preform. And we see that many of them have much better performance than either non-crimped fabric or aluminum parts. So we can get an extra 5–10% gain in stiffness compared to the optimized non-crimped fabrics, which means that we can further reduce the weight if needed, if we can, for example, change the fiber reflection, or if we can reduce the thickness of the part. So just several concluding remarks. So as in this project, we show that optimizing the mesoscale structure of fiber architectures helps to reduce the weight of composite components. and non-conventional architectures provide even more weight saving. What I didn't cover in this presentation is optimization of processing properties, such as permeability. Because you can optimize the mechanical properties, but you can arrive to an architecture which is very difficult to impregnate with resin, or when impregnated, will have a high void content. So what we want to do in the future is to create a multi-objective optimization framework, which we can use to maximize mechanical properties, minimize resin filling time, and minimize the void content. And I think I will stop here, and thank you very much for your attention.
Thank you, Mikhail. Another good presentation.